Alright, hello, I'm Joseph Johnson, and this is my presentation on edge coloring. So I figured the first thing I should do is explain what edge coloring is. Edge coloring itself can be defined as coloring the edges of a graph with various colors so that no two incident edges share the same color. So in other words, none of the edges that share the same vertex also share the same color. Now the chromatic index is the smallest number of colors needed to properly edge color a graph. This means that we don't use any more colors than we have to while coloring the edges. You can see proper notation for the chromatic index here. So again, this is the smallest number of colors needed to properly edge color a graph. So to the right here, we got this small little graph. It is got 6 vertexes. It is a connected graph, and as you can see here, the vertexes are all of degree 3. So in order for each of the vertexes to be able to take or match all the edge colors there, that means we're going to have 3 separate colors. So let's say we were trying to prove that a chromatic index that we came up with was correct, that was the minimum number of colors necessary to properly edge color this graph. So to do that, there's going to be 2 things that we're going to have to demonstrate. The first one is being that we're going to have to show that the numbers that we came up with are actually going to work with the graph that we have. So we're going to have to actually properly edge color it with the proposed chromatic index that we have. Then the next thing we're going to have to do is we're going to have to take the next smallest number, and we're going to have to basically prove that we can't use that number. So to do that, we're going to have to start working through the problem as if we were trying to properly index color it until we run into a contradiction and are able to demonstrate that there is indeed a contradiction. So we're going to come back to Vizing later to discuss his impact in further detail, but for now I'm just going to talk about his theorem. So essentially his theorem says that any simple graph's chromatic index is either delta or delta plus 1. So what this delta is representing here is the degree, the vertice with the highest degree. It's that degree. So the way we decide on whether or not it's delta or delta plus 1 here depends on whether it is a type 1 or a type 2 graph. So type 1 graphs typically include bipartite graphs and planar graphs. And type 2 graphs typically you'll see those come about whenever you have an odd cycle. I'll have a demonstration of that later on in this presentation. Right, so now I'd like to give some real-world examples on how edge coloring can be used. So the most common example I have found is in regards to scheduling, specifically with round-robin style tournaments and sporting events. It's commonly used in the NFL. So here's where I'm going over my sports team example. So typically in sports seasons or round-robin style events, there's going to be multiple matches or games going on at the same exact time. But obviously you can't have the same team scheduled for multiple events at the same time. So we have to use the edge colors to help represent these different time slots that we have. In my example here, we have supplied only 4 teams representing by these 4 vertexes with the intention that every team play each other at least 1 time. That leaves us with a connected graph. Since we do have a connected graph and 4 vertices, that means delta G, the vertex with the highest degree, is degree 3. Since we have a simple connected graph, our chromatic index is going to be equal to delta G of 3. This means we are going to need at least 3 different time slots for all these teams to be able to play each other at least 1 time. Now I'd like to talk about lower bounds and upper bounds. The lower bounds is going to refer to the minimum numbers of colors that we're going to actually need, similar to the chromatic index. So again, as I've stated earlier, we are going to look towards the vertex with the highest degree, and we're going to use that number to help us decide the minimum number of colors we're going to need. The highest degree is going to be, or for the upper bound, is going to be the maximum number of colors that we can actually put into it. It's still properly edge colored as well. To prove that an upper bound is actually correct, you have to use induction. In this case, I have the greedy algorithm, which can be used to predict upper bounds, and I'm going to go over the proof for that really quickly. And again, the upper bounds here is not being used to predict the chromatic number. It's being used to predict the maximum number of colors. So it is the upper bound. We're using the greedy algorithm to do so. So looking at the theorem here, it states that if we have a graph G with a degree delta G, then the chromatic index is going to be less than or equal to 2 times delta G minus 1. So for our proof by induction here, we're going to have to start with the base case. And so in this case, we're going to assume our delta G is 1. And then when we do our little calculation here, we're going to realize that only one color is going to be needed. And the second part is we do the same thing with 2. And we're going to realize only 2 colors are needed. So from there, we have our induction hypothesis. So any simple graph G with k less than or equal to n edges is 2 delta G minus 1 edge colorable. At this point, given our hypothesis, we're going to assume G has n plus 1 edges. Now the next thing we need to do is we're going to look at this graph example that I have down here at the bottom right, and we're going to imagine that we are removing the center edge there that's connecting to the two graphs. Now when we do that, our delta G here is going to be one less than it was before. So these two, and also these two nodes that we have at the bottom here, this one and that one, they are going to, their degree is going to be equal to delta G with just the E edge here removed. So collectively, the colors that we're going to have at that point is going to be 2 times the delta G with the E edge here removed. Now then if we add the edge back, we're going to have 2 delta G with the E removed plus 1 amount of colors, because we just added one more little edge there, and you can see all this adding up to that way. As you can see at the bottom here, when we get our 2 delta G without the E plus 1, that is going to be equal to what we had originally started with. So we have completed the induction proof. Now we're going to talk about edge coloring using cycles, and this is going to go back to what I was talking about earlier, where we have the type 1 and the type 2 graph. So as you can see here, in this case, the cycle on the left here has an even number. So you get blue, red, blue, red, blue, red, blue, red. So we know here too, every vertex is going to be of degree 2. So it makes sense that our chromatic index is also going to be 2. So it is a type 1, and that matches up with what we had stated earlier about type 1 graphs. Now over here in our odd number cycle, we end up with having to use 3. Now why that is if we just kind of go through it here, we go blue, red, blue, red, blue, red. Now if we were going to put another blue here, which would logically come in the next order, we would have an issue with the other blue being over here. So we do have to use the other color for that reason. Quickly, I wanted to talk about edge coloring with complete graphs one more time. So for a complete graph, we know the delta is going to be equal to the number of vertexes minus 1, because that is going to be the degree of every vertex on the graph, because they're all connected. So the other last thing is, if it is an even number of vertexes, it's going to be class 1. If it is an odd number, it is going to be class 2. Now I'm going to go over a brief history of edge coloring and talk about some of the people that have developed our understanding of the practice up to this point. So it was first proposed in 1880 into relation to the four-color conjecture, which is the idea that every map could be colored with 4 different colors so that all the neighbors have different colors. The first paper for edge coloring was written by Tate. Peter Guthrie Tate in 1889, where he proved the 4-color problem is equivalent with the problem of edge coloring every planar 3-connected cubic graph. So later in 1916, Dennis Koenig is the one that proved that every bipartite graph can be edge colored with exactly delta G colors. Claude Shannon here proved in 1949 that every multigraph could be edge colored with at most 3 delta G divided by 2 colors, at most meaning the worst case scenario. So down here we have a picture of what's called a Shannon multigraph. This thing is made to demonstrate the worst case scenario. So as we can see here, delta G is going to be equal to 6. So our equation is going to be 3 times 6 divided by 2, which is going to equal a 3 colors maximum. In this case, since it is going to be the worst case scenario, this is also the correct chromatic index for this graph here. All right, that does conclude my project. Thank you for watching.